Hello, we are Group 7 and our topic is stock price prediction. I'm Supriya Parthiban. Stocks are shares of a company. Buying a company's stock means you own a part of the company. Broadly, stock market analysis is divided into two parts, fundamental analysis and technical analysis. We are trying to predict the stock price using neural networks here. We'll be using a dataset from Shanghai. The dataset has 10 attributes and 6,109 instances. There are no missing values. The dataset contains the values of the stocks for each day from 1990 to 2015. Data pre-processing is done and we drop some of the columns to reduce complexity. It can also be observed that it's a time series dataset where the first row contains the oldest stock price. It would be better if you could predict the values for recent stock prices and train the models on the past price. We started with some traditional models like linear regression, support vector machine with radial basis function, random forest regressor, and gradient boosting regressor. Another machine learning algorithm that we used is k nearest neighbors. It is based on the independent variable knn finds the similarity between new data points and old data points. We also used moving average. Averaging helps us to get a better idea about the trend of the market. Lastly, we tried using auto-regressive integrated moving average ARIMA. It helps to smooth the price data to form a trend following indicator and reduces noise. The last algorithm, ARIMA, is a very popular statistical method for time series forecasting. Let me introduce you to the code. We import libraries like Panda, NumPy, Matplotlib. We first load the dataset and set the date as the index. We do some data pre-processing. We use different techniques to predict the highest price of each day of the stock. While splitting the data into train and test, we can't do it randomly because it will destroy the time component. A linear regression model, support vector machine, random forest regressor, gradient boosting regressor, all are chosen and the test and the train data is passed. Using the subplot feature, we have tried to visualize them. Their accuracy is also printed. From here, it can be seen that random forest model is the best performing one, followed by gradient booster. Other algorithms like moving average, KNN and auto ARIMA are also performed, and from all the above it can be seen that their RMS E values are very high and their prediction is very poor. So we have used neural networks. We can safely say that regression algorithms have not performed well on this dataset. The model overfits, making these not accurate. All traditional predictive regression models face significant challenges in out-of-sample predictability tests due to model uncertainty and parameter instability. Price movements of stocks exhibit noise from one moment to the next. While a given overall trend may be upward, it can see temporary dips along the way. Predicting these fluctuations and guessing their direction is a key part of the challenge we set for ourselves. To achieve this, we applied neural networks.
Now I will introduce RM part to you. Our project aims to input a period stock value to predict the trend of stock coming period. In traditional machine learning methods, all input and output are independent of each other, so they are not suitable to predict stock value. RNNs are models which can capture the dynamics of sequence, so they are powerful to deal with sequential data. This is the main structure of our. We can see that the current state is not just based on the input data, but also depend on the previous hidden layer. Every time step, the transition function is same, which makes the function learnable. And this is the main code of RN by TensorFlow. I will introduce this to you. If we want to implement multiple time steps at once, we can call dynamic RN function. Using this function, we input H0 and the sequence of input X. We can get each state H and the final state. Now I will show you the code part. You can see this is our dataset after pre-processing. First, we divide the dataset into training side and testing side 9 to 1. And the bench size represents the number of benches. Within a reasonable range, the larger the bench size makes the direction of the drop more accurate. The time step represents the length of each sequence. It determines the subset of the local optimum that the algorithm can coverage to. This is the bunch normalization function. We use it to normalize for each training mini-batch. After that, we split the features and labels in our training and testing dataset, and we get the bench index. Then we can build our RN model. First, we need to set some parameters: the hidden layer unit number, the input and output dimension, and the learning rate. After that, we need to initial the matrix of weights and binds, assign random values to them. The in represents connect the input and hidden layer, and out represent connect the hidden and output layer. Then we build the R model. First, convert tensor to two-dimensional and input it to hidden layer. Then convert tensor to three-dimensional and input it to RN cell. Next, we call basic RN cell function and the dynamic RN function, as I explained in slide. Then we multiply the weights and the binds. We can get a predicted value. Then we can train our model. First, define the loss function, and we use Adam optimizer to minimize our loss. We fit the training features and label. We run 600 times and print the loss every 10 times. We can see that after 600 times training, the loss is very small. Finally, we can do prediction using the trained model, and we also use mean square error to evaluate the performance of our model. We can see the mean square error of our model is around 0.01. We can see the true value curve in red and the predicted value curve in blue. The two curves almost coincide.
Now let me introduce LSTM model. When we introduce this model, RN suffers from vanishing gradient point problem. This problem causes RN to have trouble in remembering values of parser inputs after more than 10 time steps. LSTM is then to solve the vanishing gradient point problem in RN. LSTM has the capability of bridging long-term lags between inputs. You can think of LSTM as a special type of RNN. The key idea is to use the memory cell and gates. We can use this formula to improve it. And FT is called the forget gate vector because it determines which components of the previous state and how much of them should be remembered or to forget. IT is called the input gate vector because it determines which components of the input from HT-1 and ST and how much of it should be go into the current state. OT is called the output gate to control which components of the state vector CT and how much of it should be opted. And now I will show you our code for LST model. And for a single LST model cell, we can use its call function to perform an operation just one step ahead of the sequence time. And in this regard, TensorFlow provides this function, which is equivalent to calling time steps. And this is our train model. We use square loss as our loss function and use Adam as our optimizer, and this is our prediction model. And in this picture, we can see that the red line is our prediction and the blue line is actual data. And also we can see that in the next period, the stock has a downward trend. And next, I will introduce deep RN model. And up to now, we only discussed recurrent neural network with a single unidirectional hidden layer, and this isn't a big problem as long as we have enough flexibility to model different types of interactions. With a single layer, however, it can be very challenging. In the case of the perceptron, we fix its problem by adding more layers. And this picture is the architecture of a deep RNN model. In deep RNN neural network, there are a multiple number of hidden layers. A recurrent neural network has a feedback connection as a hidden layer. Each hidden layer unique is connected to itself and also to other nodes in the hidden layer. And so basically, deep recurrent neural network means multiple recurrent hidden layers in the network hierarchy. And we compute the hidden state of layer 1 as before, and using ST as input. And for subsequent layers, the hidden layer state of the previous layer is used in hidden place. Finally, the output of the output layer is only based on the hidden state of the hidden layer L, and we use output function G to address it. And just as the multiple perception, the member of hidden layer L and member of hidden unit H are hyperparameters. In particular, we pick a regular RNN into implement the model. And now I will show you our code. And integer float RNN cell can be stacked using this function, and the parameter is the set of the layer, and we define it into two, and the function of the output is a tensor, and we should reshape it and flow to calculate. And this is a picture is our result, and we can see that MSE is 0.019556, and it's very low. So we can see that our model is it has a good performance.
My part on gated recurrent unit, and I will do my presentation according to these three parts. I will briefly talk about the problem vanishing gradient, and then I will introduce what is gated recurrent unit and how does gated recurrent unit work. Finally, I will show the result of my program, stock price prediction with gated recurrent unit. Okay, so the problem vanishing gradient is due to the nature of backpropagation, specifically in the process of backpropagating. It is the gradient that used to adjust the network internal weight and thus allow the network to learn. That means the bigger the gradient, the bigger the adjustment, and vice versa. However, the problem is that if the adjustment to the layers before it is small, then adjustment to the current layer will be even smaller. As backpropagation is stalled, the gradient shrinks exponentially. Therefore, the earlier layer fails to do any learning as the internal weights are barely being adjusted due to extremely small gradient. That's why we call the problem vanishing gradient. And then let's see the structure of the gated recurrent unit. And I would like to divide the structure into four parts. They are update gate, the reject gate, the current memory, and the final memory. And the respective formula is also listed on the right. And notice that the formula of reject gate is the same as the one for the update gate, but the difference comes in the weight and the gate usage. Essentially, the reject gate is used to decide how much of the past information to forget by change, or by adjust the metric weight. The same principle is also applied to the update gate. And let's focus on the last formula. And from the last formula, we can see that the gated recurrent unit is able to eliminate the vanishing gradient problem by making use of the update gate and the reject gate. For example, we can change the value of J here to 1, and thus we keep almost all the information from the previous information, and 1 minus 1 will be close to 0, and thus we don't keep any information of the current memory. And last, I would like to show the result of my program about stock price prediction with gated recurrent unit. And according to the picture shown here, we can see that the overall performance of the gated recurrent unit is extremely good. And the mean square error of gated recurrent unit is also very small. It is even smaller than 1/4 of the mean square error of the standard recurrent neural network. And that's all.